let me give you a brief overview over device-independent QKD. And there's a nice old slogan from the quantum information community saying that we are the people who are turning paradoxes into products. And actually, the iQKD fits quite well into this slogan, because it's basically about turning a Bell test experiment, like one of the very fundamental physical experiments we can do in order to check for the absence of local hidden variable models. And we're turning this into a QKD system, basically a usable product in some future technology applications. I will give you only a rough overview and some intuitions on the field. If you are interested in the details, please come to us later. I will tell you roughly how QKD, device-independent QKD will work. I will elaborate a little bit on experiments, which we now have. So this is a big deal. We didn't have experiments on this for 30 years. And I will give you some outlook to future directions and recent developments in this field. So, okay, why do we need QKD? Well, quantum computers are a threat. Last week, there was a report by the, updated technical guideline by the BSI saying that, okay, you should update your crypto systems away from RSA within the next 6 years. So we have to do something. Post-quantum cryptography is one direction one could go. However, if you come from a mathematical standpoint, well, proving security under computational assumptions is quite hard, or at least not easy. And here QKD is an alternative. And I mentioned this because, well, often QKD and post-quantum is confused, but it's an entirely different technology. So the rough idea of QKD is why we want to detect eavesdropping in a communication channel. And we want to do this under the laws of physics as a basic assumption. And well, we will have several talks here about physical layer security, and I would always tell QKD as one version of physical layer security. And well, as such, we can, at least in theory, achieve information theoretic security, so security based on statistical properties of a system, and we can also have long-term security. And maybe as comparison, QKD, PQC, so well, physical layer security, so this is a picture of a dashboard of a car, and in a car you have different safety systems, and I think this analogy is, at least to some point, quite good, because while QKD should prevent a damage, yeah, like a ABS or ESP is doing in the car, and PQC is more for the case on a higher communication layer. When your data gets stolen, you want to prevent that this data can be decrypted. And well, in order where we have a dispute between QKD and PQC, and I would always say, well, like safety systems in a car, we need both. Yeah, just because you have an airbag, you don't want to get rid of your ABS, and vice versa. Okay, how do we achieve information theoretical security? Well, basic setting, we have Alice, we have Bob. Alice wants to talk with Bob. They are connected by some channel, and there's an attacker Eve in the middle. When they want to have a secure key, because when they have a secure key, they can do, for example, one-time pad encryption and get information theoretical security. What is such a secret key? Well, they want to have some bit string on both sides, which is fully correlated and provably uncorrelated to an attacker. And if they can realize this resource, well, they're happy, because then we can achieve this type of security. And we want to prove this in a statistical manner. Basic intuition, how do we prove this? How do we get there? Well, assume that you have some physical system on which Alice, Bob, and Eve have access, and they get some data out of it. Then the rough intuition one can get from information theory is that, well, if we have a certain amount of correlation between Alice and Bob, let's say n bits, and m bits between Alice and Eve, and if Alice and Bob have an advantage in their correlation, they can harvest, asymptotically at least, this advantage and extract a secret key. Yeah. One can make this mathematically precise and end up with a leftover hash lemma, and we have a quantum version of this quantum leftover hash lemma, which also works for finite block length security. Here, the quantity we have to bound is the epsilon smooth min entropy. There are now more modern versions of this quantum leftover hash lemma using sandwiched Renyi entropies instead of the epsilon smooth min entropies. This is an active field of research. What entropy has to go there in order to bound the extractable length of the key in a finite block length setting. I won't go in any detail on this. The important information here is that, well, a good bound should achieve this asymptotic limit I showed you before when the block length is going large. And especially for the QKD, where we are working with very low event rates, a good bound here is essential in order to achieve, for example, an experiment with a positive outcome. Okay, so QKD, I said we have this abstract physical systems from which Alice, Bob, and Eve can extract data. So in a quantum system, in a quantum setting, we would describe such a system by a joint quantum state, psi ABE, shared between Alice, Bob, and Eve. And Alice and Bob would do measurements on this joint state. And for the moment, Eve would just collect this quantum system in a worst case manner as a quantum memory. So Eve would not do anything with this. And yeah, Alice and Bob, they can access on the system. They can try some measurement, get some data out. And well, in an ideal world, if this system would be, the system between Alice and Bob would be a bell pair or a source that can emit IID copies of a bell pair, well, we would be quite happy because this would be the perfect resource for creating such a key. So if you have a bell pair, you have maximum entanglement. If Alice and Bob measure on this, they get correlated data. And since bell states are pure states, you directly know from laws of physics that this state must be uncorrelated to any environment, especially including Eve. However, in the real world, we don't have a source that can emit IID copies of a bell state. We have some different state, rho AB, which is usually not known and might be correlated under over many, many rounds of a protocol. Yeah. So the name of the game, if you want to do a security analysis for QKD, would now be to estimate the proximity of a real world state to our ideal state of a bell pair over n rounds. And now you have to employ assumptions in order to do this analysis, in order to evaluate this proximity. And this is where DI comes in as a setting. So okay, now we have boxes, and one can ask, okay, what do we assume about those boxes? Yeah, we can assume that we have the full description of how those boxes are functioning. This would be called device dependent. And actually, if you make those assumptions, well, QKD is a working technology. Yeah, so you can buy those devices under those relatively strict assumptions that you really know how those things are working. And this is good. Well, now there's an intermediate setting where you say, okay, I only know about one box, how it's functioning. For example, Alice makes the assumption how your device is functioning. The device of Bob is, well, somewhere out in the wild. So you don't want to make assumptions there. This is called one-side device independent. And still there, we can at least easily prove security by basically reducing this one-side device independent setting to the device dependent setting and get comparable key rates. However, if we want to go to a setting where we do not want to assume any functionality of those boxes, well, then we are doing device independent QKD. And so far, the key rates are much worse, and the technological challenges in order to implement experiment that proves some security under those, well, non-characterized devices settings. That's quite hard. Well, we need some assumptions in order to do anything. The basic assumptions are, well, we assume that we have secure labs. So Alice and Bob have a lab, and they have a magical firewall that prevents information leaking out from the lab to the environment in an uncontrolled way. In a certain way, this is a natural assumption for even holding a secret. Yeah, without controlling your local lab. Well, why would you want to talk about secrets? Yeah. Another assumption as well, you have local randomness as a resource. So you can do something in your local lab that is unpredictable to an attacker, and this will give you something like the key ingredient in order to even do cryptography. Because when an attacker can like predict everything you do in a lab, well, how should you ever end up with a meaningful protocol? And while the third assumption is we assume that quantum theory is correct. Yeah, at least in the basic version, it was presented today in the first talk. And now we want to prove security under those minimal assumptions. How does it work? How does a QKD protocol roughly work? So we have different rounds. So Alice and Bob, they have the boxes, and they can switch their boxes to different rounds. And one part of the rounds, they will extract some key or data, raw data, they will later on process in order to get a key. And there are other rounds called test rounds where they will, for example, do a bell test in order to learn something about their devices, about the functionality of their device. So Alice and Bob, they collect some data. And well, they don't want to assume anything about their devices. But well, when you do a bell test, you can, or at least a bell test with a high enough score, you can pin down a set of states which would be possible to explain the data you just obtained in your experiment. And now the basic idea of a QKD security proof is, well, you want to pin down this set of possible states that could have explained what you saw in the lab. And from this, you want to have a worst case estimate on the security of your device. Yeah. Okay, so what do we have to bound? This could be a 1-week lecture. In a nutshell, the quantity we want to bound is, first of all, the asymptotic key rate. That can be written as a difference of two conditional entropies. We have the conditional entropy between the data obtained by Alice and the quantum site information held by Eve, minus the correlation between Alice and Bob. And well, in this difference, you can already see this asymptotic behavior I showed you on the leftover hash landing lemma slide. If you have this rate, you can, at least for a device giver, estimate how well would it function in an asymptotic limit. And for most experiments, this is actually the number you're looking for, because we have finite rates need very high event rates, very good devices. But if you're already able to build a device for which you can prove that asymptotically this device has a behavior that could lead to a positive key, you're quite happy. Nevertheless, we have the technical tools in order to also do a finite block length analysis. Basic tools here are, if you want to employ an IID assumption, well, we have a quantum version of the asymptotic equipartition property that allows you to basically evaluate the difference between a finite block length setting and the asymptotic rate. And by this, you can handle the finite setting under IID assumptions. However, well, when we talk about security, we don't want to make an IID assumption. So we call it general attacks, the setting we would have here. And over the last years, we developed many different tools in order to handle this general attack finite block length setting. So just to mention some names, so we have a class of entropy accumulation theorems, and there are also quantum definity theorems. And the overall strategy in order to do a proof is always like, you start with a general attack, you apply one of those techniques of entropy accumulation, definity, you reduce to the IID case, and from the IID case, you reduce to the asymptotic behavior. And on all of those steps, you accumulate some errors, and at the end, you hope that those errors are small enough such that you can still get a positive key. The main technical challenge is in all those cases, well, you want to have a bound on this conditional entropy between the data Alice measured and the uncharacterized environment. Okay, and here some physics come into play. You can think about the measurement process from a, well, Steinspring dilated perspective, where you have a measurement process of Alice, where she's getting some data out of her state, and you can extend it to a unitary evolution, including all the systems that are involved in it. So here we have Alice, we have Bob, we have Eve, and we have some blank register on which Alice wants to store her data. Then we do a unitary evolution corresponding to the measurement process Alice is doing. And afterwards, we get a state A prime, because Alice is doing something, some measurement, but her state will change. And she will write some data into a register, and I will call this X. And well, Bob and Eve are doing nothing in the first step of the measurement process. Oh yeah, something to mention here. This is all under the assumption of one-way error correction. So Alice is getting some data. This data is declared to be the correct key, and in later stages of a protocol, Bob will try to error correct in order to get the same data as Eve has, Alice. Okay, so we have this measurement process written in a Steinspring dilated picture. And what's nice here, so you can write down a pure state for the initial state. Yeah, this is the idea of Steinspring. So you dilate everything until you end up with a closed quantum system. And well, since it's a unitary, the state afterwards will also be a pure state. Yeah, so we have a pure state to pure state evolution. And now we can split this evolution into two parts. So we have one evolution between Eve and the key register. And we have another evolution between Alice and Bob and the Alice state afterwards and Bob. And well, if you take such an evolution and if you split the system into two parts, you will create some entropy. And here the physics comes in, because the entropy you create in one part of such a process will equal to the entropy you create in the another part of the process. And now it's easy to check algebraically this quantity we want to bound, this conditional entropy. It's exactly the entropy production on the Eve memory side. And now physics will tell us that, okay, this is equal to the entropy production of the Alice afterwards Bob side. Yeah. And now the basic idea of a security proof, or the basic idea why can we even do QKD is, well, this purple evolution is only happening in the lab of Alice and Bob. So they have some access to the system before and after this process. So they have a chance to estimate this entropy production. And by this tell something about Eve, even though they do not know what Eve is doing. Yeah, and this is somehow a genuine quantum argument. So the ability of dilating a system or open quantum system into a closed quantum system is actually even valid on the level of GPTs. Whenever you do such an operation, you will end up with a quantum system. Yeah, so classically you cannot you cannot do this extension to pure state evolution without ending up in a quantum theory. Yeah. And well, I think it's quite nice because, well, this really gives you an intuition. If you go down the route of mathematics, well, this entropy production can be further rewritten in terms of a relative entropy. And so the whole mathematical problem boils down to bounding a relative entropy. And this is where it's actually getting tricky. So the meta problem now we want to solve is we want to minimize the relative entropy under some linear constraints. So those linear constraints are abstract for Alice and Bob obtain some data about their quantum state. Now the biggest problem in this whole DI setting is what are actually those states you're talking about? Yeah. So on a naive way, one could think about, well, I don't know what my box is, so this could be any state in any Hilbert space. However, as a mathematical object talking about all states in all Hilbert spaces, it's way too big. So Hilbert spaces do not even form a set, they are category, and we don't want to do category theory here. But you can employ some topology and end up with a object called, well, it's a universal C-star algebra generated by projections. And this is like a sane mathematical object on which you can talk about all states that could lead to a certain amount of data, assuming that your labs are really separate. So this assumption of separating your labs is really giving you a topology on the possible set of systems you can look about. And it's actually giving you enough structure in order to, well, formulate an optimization problem over convex sets. Without going into too much mathematical details, now we are confronted with the problem. We want to minimize this relative entropy over those operator algebras. And well, if we're dealing with real data, we can only do this numerically. So we had to develop certain technologies in order to do numerical optimization on C-star algebras, which sounds a little bit crazy, but actually you can do this. Several techniques we have to imply here. There's one nice construction that appeared 3 years ago. So we have an integral representation of the relative entropy that also extends to operator algebras by Frenkel. Based on this, well, my co-authors and I, we developed a toolbox for doing those optimizations. And what you end up with is something we call a C-star SDP. So it's a semi-definite optimization on C-star algebra. So you basically end up with a linear optimization problem on convex sets on C-star algebras, which still sounds like a crazy object, but actually there are some SDP relaxation techniques for this. Yeah, and the basic tool is you can express positivity on a C-star algebra by a hierarchy of semi-definite optimization problems. And by this, you can actually do numerics on C-star algebras and hopefully compute some key rates or this asymptotic key rate or lower bounds from this key rate, which is exactly the ingredient you need in order to do evaluation of a security of a QKD protocol. So with this, let's leave the math behind and talk a little bit of experiments. So as I said, it's quite challenging to do an experiment that shows device-independent QKD. So what you basically need, you need an experiment that has that's implementing a Bell test. Yeah, and also implementing Bell test was a big thing almost 10 years ago. So you need a Bell test with a high quality and you need a low bit error rate. Yeah, so Alice and Bob should have very high correlations. And you want to do this at a high, with a high event rate. Well, you definitely have to close the detection loophole, and you want to do this with a reasonable distance. And those are all challenges that are somehow going in different directions. So, well, as longer you make the distance, as harder it is to get a high event rate and, well, also high violation of the bell test. Nevertheless, 5 years ago, we managed to get the first experiment there. So there was a sequence of 3 experiments. So I was involved in the Munich experiment. Why is the pointer lost?
Press twice again.
Okay. Anyhow, good. Yeah. So while those experiments were done all secretly, and then the people from Oxford, they put theirs on the archive, and then all other groups also put their results on the archive. So we had those 3 papers within 1 week. This was a quite exciting week. Nevertheless, none of those experiments were able to tick all boxes. So we had one experiment in China. They used a photonic implementation. They had a very high event rate, but well, the distance was tabletop and 20 meters of fiber, I know. And the quality was quite poor. The experiment in Oxford was also tabletop. They had quite good quality, but only 2 meters distance between Alice and Bob, which is really not good if you want to do a secret. And well, we in Munich, we actually employed an experiment by Harald Weinfurter, which was used for a bell test. So we had this distance and we had the quality, but the rate was very, very low. So we had like 5,000 events during 1 weekend, which is a very small rate. And well, this was the status until last month, where a new experiment appeared on the archive and in Science by people from China, Panjan Wei. And well, the theory was done by people in Singapore, Ernest Tan, Thomas Hahn. And they did a tabletop experiment, but with 100 kilometers of fiber. Yeah, and they showed entanglement generation over those 100 kilometers, and they had a different fiber of 11 kilometers where they showed that they could do a finite key experiment. But still, it's tabletop, and we are still missing like one experiment that is showing the IQKD with really separated labs. But things are moving quite a lot now. By this, let me give you some overview of further directions. So one direction is we have to change the protocol a little bit. So some development me and my co-authors in Singapore did, well, instead of having one fixed base for key generation, one can switch the base in which you generate the key. This is called random key base protocol. It shows that by this, you can get higher key rates in total because, well, Eve now has to attack different key bases at the same time, which is giving Alice Bob an advantage. Another direction is noisy preprocessing. So Alice can make her data artificially a little bit more noisy. And in the correct regime, this will end up in a situation where actually Eve will have a disadvantage compared to Bob under this a little bit of more noise. And a very active direction at the moment is to employ local self-tests. So if you think of a topology like here, we have Alice and Bob, and now Alice and Bob have 2 friends. Let's call them Fred and George, or A1, A2, and B2. And the basic idea would be you have a router. So you can either connect Alice and her local friend, Bob and her local friend, or you can connect Alice and Bob. And now if Alice and her local friend are in close proximity, they have a much higher chance to get a high score in the bell test because, well, score in the bell test drops down with distance. So you can basically use this short range connection in order to prove that Alice has good devices and the same for Bob. And having this further information, you can, at least in a limit, self-test the devices of Alice and Bob. And by this, get a behavior that is actually close to the device-dependent behavior. And this data is actually from the last weekend. So my co-author Geron Kusman did a lot of numerics work during the last weeks. And we now have a protocol and key rates where we can show that, okay, depending on the quality of the local bell test, which is here vlog, you can really interpolate between the best known device independent bound and the device dependent bound. And while this hasn't been done in an experiment yet, well, there are several challenges in order to get there, but at least this is showing that in principle, the iQKD can reach a similar level as device-dependent QKD one day. With this, let me give you a brief outlook. While there are experiments, however, there are still many open questions. So we have to improve our numerical analysis. We have to improve our proof techniques in order to get something with a finite block length security. Well, for sure, we want to employ networks. We already heard about quantum repeaters. So the technology used for this device-independent experiments is using trapped ions or atoms as a source of entanglement. So this is relatively compatible with the network technology you need. So maybe one day when we have quantum networks, then device independence will be the standard protocol. And well, the other question is like, okay, can we get finite key from photonic technology, which would be point-to-point, but at least to this point of event rates would be much, much higher if we have a fully photonic technology here. There are some reviews. There are some recent reviews that I don't include here yet. I'm sorry for that. If you have further questions, just come to us. Thank you.
Thanks a lot, René, for this nice presentation. Anyone has a question for discussion?
Maybe, thank you for the interesting talk. Maybe educational question. Do we really need a loophole-free belt test? Or am I right that detection loophole is really important in device-independent, but locality loophole, that detections are, I'm not sure that it's called like this, that space-like separation between the events is not is important for hidden variable theory, but maybe not so important for device independent, because I don't think that somebody believes that some theory behind quantum mechanics can. So do we really need to close this type of loophole?
Yeah, you're totally right. So the basic loophole we have to close is the detection loophole. If you assume quantum theory, you assume that you have like your local separable systems. Yeah. So okay. Yeah, detection loophole is really the problem.
So it's in principle in device independent, the task is easier than fully loophole-free belt test.
Yeah, you don't have to look for well for the space-like separability, it's a timing problem in most experiments, and you don't have this timing problem in QKD. Yeah.
Okay, thank you. Okay.
Okay, is there any other question from the audience?
Okay, my question is simple, I think. So when you explain the three assumptions and you pick this QKD device dependent, is there a difference between use cases? Which use cases especially go for which assumption? And then is key rate only dependent on our technology, or with each of these assumptions, key rate is also changing, like that is why some use cases choose one of the assumptions, not the other one.
Okay, yeah. As more assumptions you have, as better your key rates are. At least asymptotically, one side characterized is as good as two sides characterized for some protocols, BB84 type protocols. Well, it depends on how paranoid you are. Yeah, if you buy your QKD devices on Amazon, maybe you want to go for device independence. The usual story would be for one-side device independence that you have a server which you trust, and then you give the other device to Bob, and Bob is going over some borders in different countries, so you don't want to trust Bob anymore. And well, in this lore, then device dependent would be a case where Alice and Bob both have servers that they trust. You don't trust the network in between. And yeah.
Thanks a lot.
Maybe some last word about rates. So we had this question about how big are the rates. So in the recent experiment in China, this was fractions of a bit per second. This is where we are at the moment. Yeah, so it's maybe enough to encode an online chess game, but not more.
Thanks a lot, René.